Hey everybody, my name is Calvin, and today we're going to be turning a tabular dataset, specifically the malt customers dataset, from Kaggle into a k-nearest neighbors graph, and we'll learn how to read it. So what does a k-nearest neighbor graph do? A k-nearest neighbors graph turns each row into a node and connects it to its k-closest neighbors. This captures local relationships that ordinary distance clustering can miss. In our demo, we'll load two intuitive features from the mall customers dataset. We'll standardize them so distances are fair. We'll build a symmetric k-nearest neighbors graph. We'll look at its corresponding adjacency matrix, measure connectivity and degree so we're not really just guessing. We'll also sweep k to see when the graph becomes connected. We'll also try a mutual k-nearest neighbors graph that keeps only reciprocal edges. We'll also build a weighted version where closest neighbors count more. And then we'll finish with a quick look at the graph Laplacian spectrum so you can see how this plugs into spectral methods. I'll explain every step as we go. To start, we're going to be bringing in NumPy, pandas, and matplotlib. Matplotlib will be used for data and plots. We'll also bring in scikit-learn to scale features and build the k-nearest neighbors graph. We'll use SciPy for the connected components and Laplacian math. And then finally, we'll use network_x to draw the edges. I've also created a few simple helpers, specifically scatter, overlay graphs, and heatmap, so we can see each step clearly. The first step is to load our mall customers dataset. I have this dataset stored in a folder called datasets. Our malt customers CSV has columns customer ID, genre, age, annual income, and spending score. For the purposes of this demonstration, we'll only be sticking with annual income and spending score. We'll start with plotting annual income and spending score because they're easy to visualize in 2 dimensions. If you look closely, we can see that the axes aren't really on the same scale. Our income ranges roughly from 15 to 140, while our spending score is 0 to 100. So the issue here is, if we built a graph now, income would dominate who counts as a neighbor. We can fix that by standardizing. What does standardizing mean? Specifically, we'll use StandardScaler. Feature scaling transforms numerical features to a common scale to improve model performance by preventing features with larger magnitudes from dominating the results. As you can see here, our axes look so much better. We range from -2 to 3 for income, and we range from -2 to 2 on our spending score. A k-nearest neighbors graph connects each point to its k-closest neighbors. To build a basic k-n graph, we can call k-neighbors_graph with parameters xs and neighbors. The mode, we'll set this to connectivity, and we'll set include self to false. This returns a sparse directed adjacency A with 0, 1 entries. That means for each row I, there are 1s in the columns of I's k nearest neighbors. Because many graph algorithms assume an undirected graph, we symmetrize. This keeps an undirected edge if it exists in either direction. The result is still a SciPy sparse matrix, which is efficient for larger data sets, and we pass it to our helper overlay graph that converts this sparse matrix to a network_x graph and draws edges on top of the 2D points. On our overlay with k equal to 10, the dense middle looks like a web of short edges, and the outer lobes are tied in by thin, stringy bridges. This tells us that K is large enough to stitch the dataset into a mostly connected structure. That's perfect if you plan to treat the data as one manifold for spectral methods. But if you want clearly separated communities, this K is a bit high. For the adjacency matrix view, we convert the sparse matrix to a dense array only for plotting a.toArray, and we feed it to a heatmap function. This is a straight visualization of the binary graph. The bright pixels indicate an edge between 2 points. Because this is just for inspection, we keep the graph in sparse format for all computations, and we only densify for the figure. Our heat map shows blocky diagonals, which means they are cohesive neighborhoods, and we also see scattered off-diagonal offshoots that correspond to the bridges we just saw. We have 2 different views, the adjacency matrix and our k-nearest neighbors graph. They tell the same story. We see strong local cohesion with a few cross-group links. However, I don't want to eyeball connectivity, so let's measure it. The number of connected components tells us whether the graph is in pieces, and the degree distribution tells us how many neighbor nodes actually have after symmetrizing. In our histogram, most nodes sit around degree 9 to 11, and we have tails at 6 to 14. That's to be expected. Interior points are a top k neighbor for many, many others, so their degree can exceed k. Combined with the sweep we're about to run, this confirms that around this k, the graph is globally connected, or very close to it. For our k, we really do want to make an informed decision. Our components curve in our run drops from 4 to 2 by about k equals 5. It stays at 2 through about 9. And then it becomes a singly connected component at roughly k equals 11, and remains there. Our average degree rises roughly linearly with k, which is about exactly what we would expect. So if we want distinctly separate customer groups, we want to keep k at 9 or below. If you want a single connected customer manifold for spectral or diffusion methods, choose 11 or above. Our k of 10 sits right at the cusp, which is why you saw those thin bridges earlier. In the context of our example, for customer segments, we may want to stick with a smaller k. We want to identify specific customer segments rather than just having it all clumped into one. Next, let's run mutual k-nearest neighbors. Mutual k-nearest neighbors is a simple, effective cleanup of our k-nearest neighbors graph. Specifically, we only keep an edge if I choose j and j choose I. For mutual k-nearest neighbors, we intentionally construct a stricter graph by intersecting directed neighbor sets. We build the directed graph once with k-nearest. We build the directed graph once with k-neighbors graph. And then we only keep reciprocal edges via a_mutual. And we run a_dir.minimum with parameters a_dir.transpose. Then we'll use our overlay graph and heat map functions to see the adjacency matrix in the k-nearest neighbors graph. Everything works exactly the same, but now we reflect the pruned, more selective graph. On our plot, the bridges thin out and the cores stay intact. So you can see we have much thinner bridges now. This component has become disconnected, while these ones have much less bridges. But we still see our main core clusters. These can represent specific customer segments. The mutual adjacency heat map keeps the bright diagonals, but reduces the off-diagonal speckles. If our goal is community discovery on this dataset, mutual at the same k can give us clear boundaries. But if it disconnects too aggressively, we can nudge k up a bit. In our graph, it might be interesting to lower k, so we can see distinct separated customer segments. Now let's turn k nearest neighbor distances into weights, so edges don't just say who's connected, but how strongly they're connected. First, I rebuild the graph in distance mode. Rather than connectivity, so that each node stores the actual distances to its k neighbors. I then symmetrize that distance matrix by averaging it with its transpose. This makes the graph undirected. From the non-zero distances, I pick a robust scale sigma as the median neighbor distance. Finally, I convert each distance d into a similarity. Our closure points gets values near 1, but our borderline neighbors shrink towards 0. Using these similarities at the same neighbor indices gives me a sparse, weighted adjacency that captures connection strength and not just connectivity. When I plot our weighted graph, the picture looks very similar to the binary version. But the heat map tells us a different story. The cluster cores glow brighter, and the bridges between clusters fade. This is exactly what I want before spectral methods or diffusion-style embeddings. Within cluster ties dominate, cross-cluster ties are weak, and the downstream algorithm can separate segments cleanly. In short, binary edges say who is connected, but weighted edges say how much they're connected, and that extra nuance makes a real difference for meaningful cuts and embeddings. Finally, we'll examine the graph Laplacian. The graph Laplacian is degree minus adjacency, and many graph algorithms start here. The smallest eigenvalues reflect large-scale connectivity. When you see a visible jump after the kth smallest eigenvalue, that often hints at k meaningful groups. We can construct the unnormalized Laplacian with CS graph underscore Laplacian with parameters a and normalize equal to false. We use the unweighted symmetric adjacency unless you intentionally want the weighted variant, and we call this function to get the smallest eigenvalues for small datasets. We're going to plot the first dozen or so to visually inspect for an eigengap. All of these steps reuse the same A that we built earlier. Only the mode, connectivity versus distance, symmetrization, and optional transformations can change, like mutual intersection or RBF weighting, change how the adjacency is constructed. Paired with our K sweep from before, the story is consistent. Below about 11, the graph prefers multiple components, but at 11 and above, it behaves like one connected manifold. We can choose K and the graph variant based on whether you want separate customer segments or a single connected view. And that's the whole build, end to end. We scaled to make distances fair, and we built the symmetric k nearest neighbors graph to capture local neighborhoods. We read the adjacency to see block structure, measured components and degrees so we aren't really just guessing, swept k to find a stable range. We used mutual edges to sharpen boundaries, weighted edges to encode strength, and we also looked at the Laplacian so you know how this flows into spectral methods. On mall customers dataset from Kaggle, we can keep k at 9 or below for distinct segments, or we can go 11 or above for a unified manifold. We prefer mutual k nearest neighbors when you want cleaner communities, or we can prefer weighted before spectral so within group ties dominate. Thank you for watching. Don't forget to like and subscribe.